Hey guys, and welcome back to the channel. Today has been a good day for some of my viewers. At least two of them have reached out to me saying they got meta offers, and one of them even called me handsome, which is how you know he was a dude. So let's go ahead and get into it. We've got another video for you all. It is a Friday. I'm going to go out after this, so I'm excited. Today we're going to be talking about Google Docs. Okay, so like I mentioned, today we are going to be talking about Google Docs. Now I assume this is a product that most of you are familiar with, but in the event that you are not, let me show off an example use case. So we've got some sort of text document, we've got one line over here that's already been written, Jordan is ... and then you've got three people over here all actively editing it at the same time. And if you're editing this document or you have it open, you can actually see other people making changes as they make them. So as you can see, we've got Kate Upton writing that Jordan is handsome, Megan Fox writing that he's sexy, Tech Lead writing that he's dumb, perhaps because Jordan called him out in one of his previous videos over all his crypto scamming. But that is another topic for another time. So let's talk about some problem requirements. I kind of made three of these, even though this could probably be summarized in like 3 words just to fill up a slide's worth of data. But the point is that more or less, if I write, you should be able to see it in real time. If you write, I should be able to see it in real time. And basically, if the document has a ton of users on it at once, all of those writes should be propagated to all of the other readers in real time. Hopefully that makes sense. Cool. And of course, another important thing is that, we don't want people to have documents that are out of sync. If I make a write, I don't want to be able to see my write and someone else can see my write, but then a third user cannot. It's important that they all eventually converge to the same state, even if it's not entirely instant. Okay, so let's go through some capacity estimates because these are going to be pretty important for what we ultimately end up discussing. So the first thing is that I'm going to keep this one abstract. I don't need to go into any specific numbers because the whole point of this problem in particular, or the reason I want to talk about it, is because I want to basically be able to design it for arbitrary scale. So with that being said, let's imagine we have billions of users, billions of different documents. You can have thousands of users editing a document at once and attempting to read it, which of course is going to be a lot of load. Each document can have hundreds of pages, and the sizes can be in the kilobytes, but frankly, if you have hundreds of pages, you could even be looking at documents in the sizes of megabytes, which would be pretty bad. So of course, if we want to be able to be processing these writes as fast as possible, both the number of writers, right? I said, literally thousands, so that's going to be really tough to actually transmit those changes from writer to writer or the writer to reader. And also the document sizes, if there are lots of kilobytes, can both be problematic. Okay, so I'm basically going to go over this problem by starting out with a really terrible solution, and then we'll gradually make them better and better as we break down what is wrong with each solution. So the first one is going to be very naive, where basically we've got client 1 over here and client 2 over here. They're both connected to some server via WebSockets. The reason we want WebSockets is so that, if I make a change in real time, the server can actually push it to the other client. And the general idea is, I make a change, right? So I send my version of the document over to the server. I grab a lock in order to do so that this guy can't send his document over at the same time, because otherwise, who wins? We have no clue. So I send over my document, it goes over to S3 or wherever the server sends it to some sort of persistent data store, and then basically it says, okay, let me look at all the WebSockets that I have for this document, send the document back to them. So it's now in step 2, going to send my document over to the other client, and the reason it needs to send it first before this client can actually go ahead and grab the lock again is so that this client can incorporate my edits into their document. So, they're going to do some sort of merging. And then in step 3, they're going to grab that server lock, and then they're going to, in turn, make the update, and then that is going to be sent to S3. So as a result of this lock, and as a result of sending out my edits to everyone else, and as a result of the WebSockets, we are actually able to achieve real-time editing here. However, the issue is it's just going to be really freaking slow. Why is that? Well, like I mentioned, the document is large, and so you don't really want to be sending it over the network every single time you make a write when all you did was type, let's say, 1 or 2 characters. Additionally, we are using a lock, and when there are locks, you can have contention, especially when multiple different people are attempting to grab that lock at the same time. And so ideally, we would like to be able to avoid both of these things. It's not so easy, but we'll talk about that later. So let's make this thing a little bit better. This is what I'd like to call a bad solution. So in our bad solution, we still have a lock, but now instead of doing anything like that, what we can do is basically say, hey, in order to make a write, grab the lock first, and then insert, let's say character A at position 3. So what's going to happen is that the server is going to lock, no one else can write, It's going to send that character to our database. Maybe it's more practical to use a database here instead of S3 because we're doing one character at a time and S3 stores the whole document. But the point is we send that character there. We then go ahead and say, okay, we now have to send that write to all of our clients. So again, we're doing this all over WebSocket. And then now finally, this guy incorporates this write, and then they can send a new write, which is going to be valid, over to the server and grab the lock once again. The process repeats. So this is going to be a lot better because now we don't have to send full documents. However, in order to avoid some sort of write conflict or merge conflict or whatever you really want to call it, we need to, again, use a lock, right? So that my changes in step 1 are integrated into this guy's document before he makes his write in step 3. And so again, there's going to be lots of contention on the lock because in reality, there's not just going to be 2 users, or well, most of the time there will just be 2 users or even 1 user. But in the really bad edge case, which is what we mostly want to focus on here because it makes it an interesting problem, you can have thousands of users writing at the same time, and you don't want their writes to take 5-10 seconds due to trying to grab a lock over and over again. So basically the idea again is that the issue with the lock is we have to process all of the previous writes in order to make our own, and to process all of those previous writes we need to make sure that there's basically some concurrency control via the lock. So what would be a better solution? So this one is going to be pretty interesting because it allows us to actually avoid using the lock. So the question is, if I write and you write at the same time, right, when we're both doing something like, hey, insert character O at position 1, that's what client 1's doing, and then client 2 is going to do insert character G at position 5. Now, if you think about it, right, if I insert character O at position 1, I go from coding, and now all of a sudden I have coding. I don't know why I made up this example. It's bad, but yeah. And so if this guy originally wanted to insert character G at position 5, right, because we had 0, 1, 2, 3, 4, 5, it would have been coding. Now, after he does that, what's going to happen is 0, 1, 2, 3, 4, 5. Now all of a sudden, if this guy's write gets processed second, we have codigen, whatever that is. And so as you can see, the order in which we process the writes actually affects where we want to insert those characters. And this is kind of the premise behind something known as operational transform, right? So operational transform is saying, hey, if I see this write, and then I see this other write, I have to actually transform this guy so that now we're no longer inserting that character G at position 5, but we're going to do it at position 6. Now you might say to yourself, wow, there must be a ton of edge cases here. And to be honest, there probably are. But fortunately, there are engineers with no lives who have actually managed to tackle those for us. So operational transform is something that has actually been utilized by something like Google Docs for many, many years in real life. So for example, let's try and demonstrate it via a diagram. We have some sort of centralized server, right? And the idea here is that if I'm sending over write number 1, and this guy is sending over write number 2, but on his client it's saying, hey, I've not seen write number 1 yet. I've only seen up to write 0. So then the server is able to say, oh, you know what? If this guy hasn't seen write 1, he needs to incorporate write 1, and that means we need to transform write number 2, as if write number 1 had come first, and that is going to give us 2 prime. And so what's now going to happen is that we'll say, we're going to send 1 back to this guy and 2 prime back to this guy and 1 back to this guy and 2 prime back to this guy. And then, we can have some sort of client-side optimization such that this guy sees his write until he receives the actual one from the server. And, we don't need to talk about that too much. But the point is, we do have to transform writes depending on the order that they come in. And each client is going to have to keep state of how many writes it's actually seen so that we know whether or not to transform that write on the server, right? So hopefully that makes sense. However, even this, while it is a completely feasible solution that has worked for many years on the Google Docs team, it does have some issues. So for starters, we basically need a server that has to see all of the writes. So what does that mean? This is kind of the same concept as something like single leader replication, right? Where as long as all of the writes go to that same single leader, everything is in good shape. However, as a result of that, this single server can become a bottleneck. And so, if we now have this guy over here, and this guy over here, and this guy over here, and they're all submitting writes over to our server has to order them all, which means it's going to have to perform some amount of locking, right? It's not going to have to force everyone to wait for an incoming write to come in, but it is going to be bounded by both its like literal networking capacity and also just using something like a blocking queue. And so as a result, this server might not be able to hold up properly if we genuinely have thousands of people writing to it at the same time. So now this is where we're going to start getting real complicated, right? Because I made this video once already. It was complicated enough, and then I decided to make it even more complicated. So let's try and walk through it, and we'll do the best that we can. So if you recall, I love talking about CRDTs on this channel. The reason for that is because Martin Kleppmann loves talking about CRDTs, and I love Martin Kleppmann. That's the guy who wrote DDIA for reference. But generally, the idea is that as opposed to having to send every single write through a server, it would be great if we could send data from place to place in a manner such that not every single server needs to actually see every single write. Obviously, every client has to see every single write, but if we can have 3 servers instead, and you randomly send a write to one of those 3 servers, and then one of those 3 sends them to all the clients, that would mean that we could then support a lot more writes at the same time. So that is the idea behind using a CRDT here. So we want to use something called a text editing CRDT. But before I go into that, let me remind everyone what a CRDT is. So a CRDT is basically saying, hey, I've got some data living on all of these different servers, and even though right now all of those servers may seem different states, when they eventually communicate with one another, they'll all converge to the same state, right? So I've got node 1, node 2, node 3. I've got state prime, state double prime. And when these guys all eventually end up, sending their data to one another, they'll all converge to state triple prime or something like that. So hopefully that makes sense from a very abstract point of view, but we'll start talking about that a lot more concretely in the coming slides. Cool. So a high-level overview of what we want to be doing with CRDTs is, like I mentioned, it is going to allow us to have more write servers. So, imagine we've got these 2 guys writing at the same time. They don't actually both have to go to this server A over here. In fact, one of them can go to server B, one of them can go to server A. We can then basically just multicast or use WebSockets or anything like that. The point is we can send the write out to every other one of our clients, and as long as they both get, or as long as all of those clients get the write, it doesn't actually matter what order they come in. We can just merge them together using our CRDT merge function, and then we'll all eventually converge to the same state. Now again, I've said there's some sort of merge function. Obviously, I'm going to have to define what that merge function is for a text document, but the idea is, if this guy is saying O at position 2, and this guy is saying A at position 1, there is some sort of merge function that it actually won't matter what order these writes come to you in, and you can all basically end up seeing the same document regardless of their order. Cool. So now, in order to start defining what our CRDT is going to look like for these text documents, I'm going to cover the concept of a state-based CRDT versus an operational CRDT. So a state CRDT means we're actually sending the entire state of what it is that we're trying to maintain. And in the case of Google Docs, we're trying to maintain a text document. So what that would mean was, if I'm a client and I make a write, I take my updated text document and I send it to either the server or to every other client. It doesn't really matter. It just has to eventually get to every single other client. So I would send that full text document. And then we would have a merge function that takes the 2 versions of text documents, right? So if I have my own local version and I get an incoming version, I have to have some sort of merge function. You can almost think of this like the Git algorithm to literally merge 2 files in code. And the idea there is that that merge function has to be commutative, associative, and idempotent. So what that means is, if I receive your file or you receive my file, we have the same result. And if I receive your file and then I receive your file again, I get the same exact result as if I had just received it once. That means it's idempotent. So the one issue here is, again, like we can do this, right? If we use something like a git merge function with our text documents, we would be able to resolve those changes, and I could just send my file to you and then you would merge it in, and I could send my file to you again and you would merge it in and it would be the same. However, this is going to be tough because the document is big. If we have a 100-page document, I don't want to have to send that to every single other reader of the document. That's going to be really rough, and it's going to make for a bad day. So what could we actually do instead? Well, we've already talked about this quite a bit this video. we're better off just sending the operations that we do on the state. So in this case, the operation is going to be insert x at position y. Now, again, we still need to define ourselves a merge function that is going to be commutative, right? So it doesn't matter the order that you receive these operations in, and also associative, which is similar. You can go look up the math function because I'm blanking on it at the moment. Anyways, the point is, with these operational CRDTs, one problem with them is that they aren't idempotent, right? If I receive the operation insert x at position y, and then I receive that operation again, how do I know if it was the same operation as before, or someone's actually just inserting the same character at the same position again? It's not exactly easy to tell. So we have to do a little bit of extra work to actually make this thing idempotent. So if that I'm a client and I receive this insert x at position y, I don't apply it for a second time. So we're going to need some additional metadata with each one of these operations. And then additionally, the question is, how can we actually make these character insertions commutative? So the problem with that is, if you recall, all the way back to our operational transform thing, it actually depends what order these guys are processed in. So if I said insert G at position 5, and then I said insert O at position 1, then what would actually happen is I would go from codin to coding to coding. And that's actually what we want. So that's a different result than if I process them in a different order. So keep in mind that order does actually matter for these insertions. How can we make it so that order doesn't matter? And that is where our merge function is going to come in. So actually, we're going to change the way that we define our document a little bit. So the first thing is that rather than giving every single character in our document an index from, like an integer index, so 0, 1, 2, 3, 4, 5, actually what we'll do instead is we'll take the first character in our document, assign it to position 0, the last character in our document, assign it to position 1, and then from there, we take every single other character and basically evenly distribute them out along that 0 to 1 timeline. So, for example, if we have 4 characters, we would have C, D, and G. D is going to be at 0.33, N is going to be at 0.66. So now what's going to happen is now someone else comes along, they want to insert a character. So if I want to insert O between character C and between character D, I actually take these two numbers and then I just divide them by 2, right? So that's actually going to put me at, let's see, 0.165. And so this is where I'm going to be inserting position O. So I would say O at 0.165. And that's what I'm going to write over the network. Insert O at 0.165. Cool. And then the same thing over here, if I wanted to insert I between D and N, I would take 0.33, 0.66, split them in 2, and that's going to obviously be 0.5. So now all of a sudden I have I at position 0.5. Now, one thing to note is that you can actually add a small random jitter. So maybe instead of doing 0.5, I do 0.5012 or something like that. Because that way, if someone else wants to write a character, coding like that, their random jitter puts them at 0.5024. And that way, it's actually deterministic whether E is going to be in front of I or not, right? So if I say write at 0.5024, now I know that every single client is going to deterministically know that E is in front of I. If I had them both at 0.5, then it's possible that some clients would have E after I. It's possible that some clients would have E before I. But if you think about this, what's actually happening here is when we do this bisection, if you think about it, it doesn't actually matter the order in which the characters are inserted, right? Because regardless of whether this guy goes first or this guy goes first, O is still going to be at position 0.16, and I is still going to be at position 0.5. And so this is the basis behind how we would model a text document in order to make a CRDT of it. However, this is not entirely easy, right? There's still going to be some edge cases here. So let's imagine one that's called interleaving. So this is one that Martin Kleppmann talks a little bit about on YouTube. But the idea is, let's imagine I want to write the word cat. Right, so assuming there's nothing in the text field so far, we just have some start and end character at 0 and 1. The characters for cat would be at 0.25, 0.50, and 0.75 because we're distributing them evenly. And then if someone else is writing bird, we would have the characters 0.20, 0.40, 0.60, and 0.80. And keep in mind that basically the idea is we want to organize these characters over the number line. So that would mean, we've got B at point 20, C at point 25, I at point 4, and on and on and on, missing this pattern. And so what's basically happened is because we've tried to insert two words that are slightly different lengths at the same place in our document, the characters actually get interleaved. What we would want is to just have, cat bird or something like that, or bird cat. Now, fortunately, there are a lot of researchers who have devoted a good amount of time to working through all of these edge cases, and ultimately, text CRDTs have now gotten in a pretty good spot such that you can effectively, follow some sort of function that when you type a character, there's some client library on your machine that converts it to the appropriate operation for the text CRDT, and then as soon as they've converted that to the appropriate operation, you can send that in any indiscriminate order to all other clients, and they will be able to reconstruct the state of the document that looks exactly the same as yours, which is really, really cool. Now, the last thing that I wanted to talk about is going to be idempotence, because I mentioned that, assuming that I send you an operation, insert X at position Y, if you receive it multiple times, are they unique writes or are they the same writes? So how can we actually ensure that they are different? And this is going to spiral into a whole deep discussion, so let's see if we can go ahead and follow it. Okay, so again, I receive a write as a client. Have I seen it before? Have I not? How do I know? Well, for starters, one approach that we can take is that each write could have an associated UUID with it, and then I locally just keep some sort of set of UUIDs that I've seen, and assuming that I have not seen it before, I apply it, and assuming that I have seen it before, I don't. And that's going to work. That's totally fine. But now for every single character typed or every single write done, I have to store an additional UUID. Now, UUIDs aren't that small. That could be another 16 characters or possibly even more per write. So it could actually be significant overhead. Another possibility would actually be to use something like version vectors. So version vectors I've discussed pretty extensively on this channel, more so in the concepts videos because they aren't too relevant for most problems. But the idea of a version vector is that, if I see a write with a smaller version vector than the version vector that I'm currently holding on my client, I know that I've already processed that write. If the write has a bigger version vector than the one that I have stored for my local document, then I have not processed it. So we can talk about this in a second. How does it actually look in practice? Let's go ahead and make things concrete. Okay, so I am going to now define some weird, slight sort of kind of version vector just to reduce a little bit of the space overhead when sending these writes over the network, but I think it does still work. So let's imagine we've got two clients, number 1, number 2, and 2 servers, A and B. And actually we've got a third client over here. So let's imagine that this guy is going to make a write to server A. The write is going to be basically given the sequence number A1 because it's the first write that's been processed by server A. We also have this guy writing to server A, and since it gets there after A1, it is going to be labeled A2. Now keep in mind that in our CRDT system, we can have writes being processed by multiple different servers. That's the whole appeal. It's going to allow us to ensure that we don't have any bottlenecks when making writes. So that means this guy over here can now make a write to server B, and because it's the first one processed on server B, that is going to have the index B1, or the sequence number B1. Okay, so like I mentioned, we're just going to assign every single write an ID based on the server that processed it and how many writes that server has processed. So A1, A6, A10, B1, B20, doesn't matter. And the reason we're doing this is because, for example, a typical version vector would look something like this. So A1 would look like 1, 0, because there's 1 write to the first server, 0 writes to B. A2 would look like, 2, 0. But we don't really need all the information of other servers, right? Because the point is this version vector actually gets bigger as there are more number of servers that can process our writes. And we really only care about actually what number write this is on one particular server. So it's going to save us a little bit of space to represent writes using this kind of server sequence number. It's almost like a Lamport clock, really. So the idea is we're going to save space compared to the typical version vector, which is a vector, whereas this is more of a Lamport clock. But eventually we are still going to have to use actual version vectors, so I'll talk about that in a second. But the problem with version vectors is they have a length equal to the number of servers. So if we had to actually send that over the network with every single write, let's say we had 20 different servers processing writes for this given document, that could get pretty hefty. Cool. So now, how are we actually going to use this on a client in order to make sure that we haven't processed a given write before? So let's say this client is me, and the first thing that's going to happen is I see write A1. I process it. I haven't seen any writes from server A before, so I'm good to go. Then I see write A2. Now all of a sudden I know that I've seen 2 writes from server A. And then finally, if I see A1 again, I will know that that's a duplicate, because right now I'm actually going to keep a local version vector, which looks something like this, 2, 0, meaning I've seen 2 writes from server A, I've seen 0 writes from server B. So if something comes in like A1, I can look at the A index over here, say, you know what, I must have already seen this already, and now I'm good to go. Cool. However, we are going to have to continue this a little bit. So the issue is that we're not actually guaranteeing the order in which writes are getting to the client. So even though they're all being processed by A, the first time around, I'm not actually saying how this write is going from A to, say, this guy over here. It could go through B, it could go over here, it could go over multicast, it could go over UDP. It doesn't really matter. The point is, I'm trying to make a system that is completely arbitrary in terms of the number of servers that accept document writes and also how those servers communicate with one another. Now, if I made some sort of guarantee where every single time a server received a write, it would just synchronously go and transmit that write to every other client over TCP, this type of thing couldn't happen. But if I don't, what could happen is that, I could write A2 over here, and then what could actually happen now is this guy sees A2 before it sees A1. And that would be a problem because, now I would increment my version vector to 2, 0, and if I were to see A1, I would think it was a duplicate even though it isn't. So how can we avoid actually receiving and processing those writes out of order, right? So this is what we're going to be talking about over here. So let's imagine I am over here. This is me. I'm maintaining some sort of document. And in order to get the state of this document, I've seen 6 writes that originated from server A. I've seen 9 writes that have originated from server B. And I've seen 4 writes that have originated from server C. Now let's imagine, just randomly, I happen to get a notification that, hey, write C6 has just come in. Well, the issue now is, wait a second, I can't process C6. I haven't seen C5, and I need it. So what can we actually do in order to get it? Well, that's the question. But again, the idea is, it is possible, depending on my network topology of document writing servers, that I could receive a write like C6 before I receive a write like C5. There are ways to avoid this happening by actually just using guaranteed ordered messaging through TCP and having every single write server instantly send that message out to every single client. But again, I want to make this as flexible as possible because I don't want these write servers to become a bottleneck. I want to make writes as quickly and seamlessly as possible. So again, we have choices to do TCP versus UDP. We have choices on, which write server is going to, write to another write server, which is then going to forward those messages out to clients. These are all things that have trade-offs, and honestly, we could probably discuss them for an hour. You could do like a round topology where you pass the messages from one server to the next, to the next, to the next, and then to clients. There are many different things that we can do here, and the point is, I want to come up with a solution that is robust regardless of what order the messages are delivered to the client in. Cool. So let's actually go ahead and keep talking about that. So like I mentioned, you can receive messages out of order. And when we do, what we can do is actually go ahead and when we first make a write, we can persist it to a database, right? So we want to be sure that none of our writes are actually getting lost. The reason being that ultimately if I need to get a write because I haven't seen C5 over here, then I want to be able to actually just request it from some server. So we'll talk about that in a second. But the idea is, here's me, I'm writing. I write to server C, apologies for the ambulance. I write to server C, and right before server C actually sends this write out to the clients, it is going to put this write C5 over in a database, which I'll just call the writes database. And then after that, it can actually send to everyone else as necessary. So we now know that C5 is guaranteed to be in a database before a single client even sees it. And so now what's going to happen is, let's say I'm this guy over here, and I've seen C4. And all of a sudden, for whatever reason, I see message C8. I can't process this thing yet because I'm missing C5, C6, and C7. And I know that if I'm seeing C8, it means that this server over here has already put it in a database and gotten an acknowledgement back because of the fact that I'm waiting on that acknowledgement to send this write to everyone else. So if I see a write, I know it's already in the database. And now if I really need to, because C5, C6, and C7 haven't come in yet, I can just request them from the database. So hopefully that makes sense. Ideally, you should just be receiving most of these writes from the server, but occasionally one might get dropped and you might not receive it, and then you can just pull it from the database. Cool. So another small thing to note is, if this database is actually indexed by both the server and the number of the write, it could make your reads a little bit faster. So if I have C1, C2, C3, and they're all ordered and sorted, that is going to make fetching C5, C6, and C7 a lot faster than having to do a linear scan through that table and just looking for all of them individually. Cool. So the reason I also wanted to talk about that was because it is relevant for new clients, right? So it's great when you're connected to all of the write servers the whole time and you can just hear writes as they come in. However, if I'm a new person and I haven't been writing to the document and now I need to load a snapshot of the document so that I can start getting the active changes to it, I have to be able to fetch it from somewhere. Cool, so how is this actually going to work? Well, the first question is, can we read it from our writes database, right? Can I, from that writes database that we discussed in the last slide, recreate our document? And the answer is yes, right? Because I know that all of the writes from server C are going to be in here. There might be a server A database, just like that, and I can read those. There might be a server B database. And so what would have to happen is my client would have to read from here, here, and here in order to get all of those writes, assuming there are 3 different write servers. And the problem with that is that even though it works, it is going to be slow. Because as we know, when we're trying to make a quick write, having to do some sort of aggregation over multiple different distributed nodes is always going to be pretty tough. So the idea is that in addition to that, besides having to do like an aggregation, we would also have to actually sort these writes by character. Because right now they're sorted by the order that they came in. But this could have like character 0.56, this could have character 0.21, this could be 0.99. And I'll make that more concrete in a second. But ideally, instead, what we want to do in order to simplify this problem a little bit is use derived data, because reading from those writes tables is probably just going to be too slow when we're first starting up. So what would be a little bit better? Well, let's say I'm a writer. I want to write to the server. So I make a write saying insert x at y. Okay, the writes table is now going to say, hey, this was write C5, insert x at y. And then from there, what we can use is change data capture to take this write and actually transform it into a better format for us to then read it down the line. So now, rather than saying, hey, C5, insert x at y, what we can do is put it into this document snapshots table, right, which we're going to be deriving via change data capture so it stays consistent. And then from there, once we actually do that, now as opposed to having C1, C2, C3, like that order, we would actually have, character 0, character 0.1, character 0.2. And so it's going to be a lot faster to read that database. We don't have to resort the characters. Now I know that's all a bit abstract, which is why I decided to write it out in the next slide over here. So now we're going to actually visualize those 2 database schemas. So we have the writes table, which is what we synchronously write to every single time that we want to make a new write to our document. And then we have the document snapshot table, which is going to be derived from the writes table via change data capture, CDC. So let's imagine that we've written the word Jordan, right? So let's say R is the first character that's getting written that gets put at 0.5. Then, we put in O at 0.25 and at 0.75. Oh, J gets put between the starting character and O, so it's at 0.125. Then we've got A at 0.625 and D at 0.56125. Now again, if I wanted to recreate the whole document, I would have to take all of this and I would have to sort it by this column right here, which is again going to be O of n log n to the number of characters in our document. And if you have a 100-page document, that is not trivial. Additionally, if our document is partitioned, then it's really not trivial because now we have to go to a bunch of different partitions, and it's probably partitioned like this, right, where each server is writing to the same database. And so now we have to fetch these guys, then we have to fetch these guys, and then we have to actually sort them. And let's say we only wanted to fetch, out of an 100-page document, we wanted to fetch the first page of our document. Now I have to actually fetch all of these guys, do a full sort on this column, and then only take the first page of it, which is maybe these two values, right? Or not even those two values. It would be the J and the O. So I'd have to do all this sorting of a huge document only to then, have to only take a small chunk of it and do that over multiple different nodes. On the other hand, if I wanted to do this in our document snapshot table, it's going to be a lot easier. Why is that? Well, as you can see, all of our characters are actually ordered by their index. As you can see, it's clearly a lot easier to just read Jordan here as opposed to having to have it all jumbled up on the writers table side. And so now, let's imagine, instead of having just 6 characters here, I had 1,000 characters and I only wanted to load the first third of them. So I want the first page. Well, what I could do is partition my document actually by the range of the characters, right? So the first third of them are going to go on one partition, the second third are on another partition, the last third are on another partition. Hey, now I only want the first third of my document. I just go read this partition. And that's super easy to do, as opposed to the other solution where I have to load everything and then sort it. So hopefully that makes a little bit of sense for the logic behind why we want a document snapshot table. So what does this general process look like for new clients that are starting up? Well, the first thing that's going to happen is we're going to subscribe to changes, right? Because we want to make sure that when we subscribe, we aren't going to be missing anything. So now what might happen is, we might get something like a C5 write before we've even actually fetched the document from our document snapshot database. But because we don't have, the precursor writes, we aren't having C4 yet, we have to go fetch that. So now we're fetching that from the database. And what's going to happen is we now get a snapshot of the database with our version vector associated with that snapshot, which is, hey, we've seen 10 writes from server A, 12 writes from server B, 3 writes from server C. And now, remember, I just received C5, so I'm saying, shoot, I need C4. Where can I go to get it? I can go to the writes database. Give me C4, C4 comes back. Now all of a sudden I'm completely caught up and all subsequent messages will come from the write servers. So this is a way to guarantee that we will never drop an individual write. Once we get our actual document state, there's no race condition in which we can, somehow miss one of these writes and then never get it back. If we do miss a write, we'll know because we'll see a higher one coming in, and then we can request the miss write from the writes database. So think of this sort of like a Delta protocol where this is like your state, and this is your operation poll, and this is your operation push. Is this a bit over-engineered for Google Docs? Maybe so. If we want to make an arbitrary type of real-time editor where you can have as many write servers as you want, communicating with each other in whatever method that they want to communicate in, whether that's multicast or a star method or any sort of just around-the-world method, it doesn't really matter. The point is that using a solution like this will ensure that we all are going to converge to the same state, and we're also not going to be doubly applying certain writes. Cool. So the last thing I wanted to touch upon quickly was, Jordan, you've made this whole over-engineered solution. Couldn't we just do this with just a document snapshot database? And the answer is actually yes, you could, right? So, if this is server A, server B, and server C, and these guys are set up so that any of our clients can make writes to them, insert X at Y. What we could actually do is just, store our document state in here. So again, it would be like first you write to the document database, and then second you can propagate that write out to the world. And that would work. It would work just fine. However, if you think about it, guess what's a bottleneck now? Our database. So it used to be the case that, just having one server was a bottleneck. Now we have many servers, but just one database. And so making sure that we actually have this kind of 3-pronged system of as many servers as we want, as many write databases as we want, and then a document snapshot database. Keep in mind the document snapshot database is updated via change data capture, which means it can go as slowly as we need it to. So it's not going to become a bottleneck. we actually have a pretty robust system here. Cool. So the last question is going to be, we have this document snapshot database down here, and the question now becomes, where is this version vector coming from, right? We need to actually be able to store this with the data. Well, there's a couple things that we can do. For starters, we can basically reconstruct the version vector from our write IDs. How would we do that? Well, if I go back up here to the schema, I could do a linear scan down this table and say, okay, well, the highest write from B that I've seen is 3. The highest write from A that I've seen is 3. So our version vector is actually going to be 3, 3. Now that's feasible, except it's pretty darn stupid if our data is on multiple different partitions, because then all of a sudden we have to make some sort of distributed transaction because one of the partitions could change after we've already queried it. It actually gets pretty complicated. So maybe that's not actually going to be the best thing to do. What we could do instead is actually keep a separate version vector table for our document snapshots, right? So now we're getting even more complicated here. Instead of just having a document snapshot table, we're also going to have a version vector table. And so what this is going to allow us to do is, as long as it stays in sync with our document snapshot, we are in good shape. Otherwise, the client gets messed up, right? So if I say, I just loaded a document snapshot with a version vector that's less recent than it, now all of a sudden I might end up applying double writes because, my document, I'm going to basically see a write coming in. I have already incorporated that write into my document snapshot. However, the version vector is telling me that I haven't incorporated that write, so now I'm going to double apply it. Or another bad thing would be, okay, so I have a really recent version vector, but a not recent document snapshot. Now all of a sudden, I'm going to see a write that comes in. It's not reflected in my document snapshot, but my version vector is telling me that I've already seen it. Now I never apply that write. So again, it's really important that we keep these two in sync. And you guys aren't going to like this one, but we're actually going to use a two-phase commit. The reason being that, again, like I mentioned, when we have something like derived data that is going over change data capture, I don't really actually care about keeping this thing that fast because it's not in the critical path, right? The critical path of me being able to submit a write as a client is just these two guys right here. Anything happening over here can be nice and slow. And that includes the two-phase commit. So what's actually going to happen now is we've got our version vector store. We do some, we have some intermediary server that's reading these events and then two-phase committing over to these two. Cool. So I think that covers everything that I wanted to cover just about. I've over-engineered the crap out of this thing as I love to do. And as a result, now we can just have as many write servers as we could possibly want in our life. Submit one write to literally any of them, send it around to our heart's content, and then everyone should be in good shape. So we've got our write cluster servers because this guy is going to be the writer. This guy is going to be the reader on the right. And so we can submit a write to any of these servers in our write cluster server. The first thing that it actually has to do is go submit to our write databases. And the idea here is it doesn't really matter how we partition these things, but it's going to be super useful if we make sure that basically, if I have A, all of the writes from A should go onto the same server because this guy at some point might request a bunch of different writes from server A to catch up. And so as a result, it would be great if they're on the same location. It would also be nice if these guys were writing for the same document and we're on the same server, but they don't have to be. Again, I'm typically just going to be requesting for one server at a time, and so as a result, we can partition by this server ID. It would also be nice if we index on the right order, because let's say C8 comes in and I've only seen C4. Now I want C5, C6, and C7. It would be a lot faster for me to know exactly where those are if those numbers are sorted in our database. Cool. So the next aspect of this is this guy can now go sending out writes, in step 2 to their heart's content. They can send them to all the other clients as they please, and the clients can go merge them in. They're a CRDT, so it doesn't really matter what the order is going to be when they get there. Okay, so this is going to be our critical path right here, everything on the bottom left. And now what's going to happen is we also perform change data capture, where we take all of the writes from our write database and we actually are going to convert them into document snapshots. And the document snapshot has two components. It's got the version vector associated with that document snapshot, and it is also going to have the document snapshot itself, where a document snapshot is just going to be all of the characters in the document, but just ordered in terms of their index in that document. So that way we can actually partition them by the range of the index of that character, and it's going to allow us to, just say load one page of the text document at a time, which is going to be really nice. Cool. We can also, of course, get that version vector, and that's going to allow us to know the version vector corresponding to one particular document over here. The one thing I should note is that I thought it would be kind of useful to use HBase for our document snapshot database. The reason being that there's probably going to be a decent amount of metadata associated with each write, and to keep reads as possible, it would be great if we could just grab the columns that we care about, which is just going to be the character and the position that the character is at. So HBase I think could help a little bit. In practice, who knows, you'd have to run a bunch of benchmarks. Cool. And then finally, the last aspect of this puzzle that I haven't really spoken about because it's kind of a given for any problem like this is a cache. If there are certain documents that tons of people are opening up per day, we probably want some sort of LRU in-memory cache to actually store all of those characters and their positions. We can just do that in Redis. You can pull these in as we're trying to read them and then use LRU to make sure that the unpopular ones get evicted and the popular ones stay in there. So to actually go ahead and read a document, just to reiterate, the first step is going to be that we would get its document snapshot. So 1A and 1B is going to be reading from these two guys. Then all of a sudden I have a snapshot and the version vector associated with it. I can start subscribing to these servers over here, the current write servers. I'm going to receive a write, and then I'm going to say, shoot, you know what? I might be missing a couple of writes. Let me actually reach out to one of these write databases over here to catch up. And then once you're caught up, you're good to go, and you're finished. Well, guys, that was a lot. I didn't really focus nearly as much on the actual write ordering and version vector stuff in the last video, but I actually think it's quite important because when you have a CRDT like this, actually making sure that you don't lose any of the writes and you don't double apply any of the writes is a bit of a struggle. So with that being said, I hope you enjoyed the video, and I will see you in the next one.